Hello. So in this example, we're going to determine if this function is continuous at the given point. So in particular, where x is 2. So again, for continuity, the things we need to check, right? We need to see if the function exists at the point given, which we can actually see just by immediately looking at this, right? So I'm looking at x going to 2, which is going to be in this top line, right? Because that's where x is less than or equal to 2. So I know it's going to be going in here, and that's just a polynomial, which is defined everywhere, meaning when I plug in 2, I'll get a nice value. So I do know that the function of f exists at 2. I'm going to have to actually compute it out later, because remember that for continuity, I need to see if the function exists. We know it will. I need to know that the limit exists. That's definitely not clear just looking at this. But then I also need to know that those two things are the same. So I'm going to have to compute them both, even though I know already the limit exists. I'm going to need an actual value. But again, since I know that the function exists, even if I haven't computed it yet, I'm going to actually go ahead and skip to the limit part, or start with the limit part, because if I can show the limit doesn't exist, I don't have to do any of the other stuff. Okay? So, as is sort of normally the case with these piecewise defined functions, when I want to check the limit, I'm going to have to break this up into a left and right limit, because inevitably this point, this, x equals 2 that I'm interested in, it's going to land right as one of these transition points between the two different lines. So I'm going to break this up into the limit as x goes to 2 from the right of f of x. And eventually, let's say over here, I'm going to have the limit as x goes to 2 from the left of f of x. Okay. So I'm going to compute both of these things, see if they're equal. If they're not equal, it means the function doesn't exist there. If it is, if they're not equal, it means the limit doesn't exist there, which means it's not continuous. But if they both exist and they are both equal, then the limit exists. I have to keep going from there. All right, so 2 from the right means 2 being a little bit bigger. So in particular here, right, I have x is a little bit larger than 2, means strictly greater than 2. That means I'm going to be in this second line, meaning I'm going to be using this equation. So this means that this is equivalent to taking the limit as x goes to 2 from the right of e to the x minus 2 plus x plus 6. Okay? And again, now that I've determined which one it's in, I don't have to worry that f of x is a piecewise defined function. I can just write sort of looking at just this and solve just that problem. So again, that's what I'm going to do. And I'm going to notice real quick that this is an exponential, which is defined for all real numbers, and a polynomial, which is defined for all real numbers. And both of these pieces are continuous on all real numbers, meaning that this whole thing is continuous. So that means that I can evaluate the limit just by plugging in. Again, typically with limits, if you're not sure what to do, you want to plug in not because it'll work per se, but because it will usually, when things go wrong, you will be able to tell where to go from there, right? How it goes wrong usually tells you what to do. But in this case, this is nice and continuous, so I can just plug right in. So this is going to be e to the 2 minus 2 plus 2 plus 6. So this is e to the 0 plus 8. And remember, e to the 0, right? So it's a nice finite base. E to the 0 is 1. So this is really 1 plus, oops, it's getting ahead of myself. Sorry. This is 1 plus 8, which is really 9. Okay. So that was that time. So now I'm going to do 2 from the left, meaning 2 slightly less than 2, right? So I'm looking at my lines. I see, okay, x is slightly less than or equal to 2, means that I'm going to be using this top one up here, right? So this means that I have x squared minus 3x plus 11. Okay, so again, I look at this and I say, okay, this is a nice polynomial, and so it's going to be defined for all the real numbers. It's continuous across all the real numbers. So I can just go ahead and plug in 2, which has this sort of added advantage, right, that when I plug in 2, it's going to be the same as computing f of 2, because that's where, right, this is where it equals 2. It's x less than or equal to 2. So that'll actually compute the f of 2 for me while I'm at it. So, asterisk here, there's a mistake that I've written. So pause the video for a second, see if you can see what it is, if you haven't been yelling at the screen already. Bad math person. So I've made a mistake here. I'll pause for a second, let you see if you can find it. Okay, so the mistake that I made is that I said this limit as x goes to 2 of f of x is a function, but that doesn't make any sense, right? Because it should have a number if I actually evaluated the limit. What I meant was to have a limit in here, right? So in particular, erase that. So in particular, I needed that the limit as x approaches 2 from the left of x squared minus 3x plus 11. Okay. So again, this is a good thing to be in the habit of, is to check every once in a while and make sure that the notation makes sense, because usually if you make a mistake at this level, the notation almost tells you, right? Like I looked at it and said, I had a limit, I don't have a limit, but I still have variables. That's a problem, right? So this tells me that I forgot to write something. In this case, I forgot to write the limit. Okay, as I was saying, polynomial, I can just plug in because it's continuous. So I'm going to plug in the 2. Now I'm just computing my way down, so 2 squared is 4, minus 6, plus 11, which is negative 2, plus 11 is 9. So this computation told me 2 things. It told me the limit as x goes to 2 from the left is 9, but also just plugging in 2f, right, because this is x less than or equal to 2, means that I plug in 2 to that function, which is this function, which would be this, tells me that the function is 9 as well. So this also tells me f of 2 equals 9. Okay, no need to do more work than you need to do. Okay, but this now shows me, right, that the limit as x approaches 2 from the right is the same as the x approaching 2 from the left. That tells me the limit exists and equals what they equal. So the limit equals 9, right? And since these two are the same, the limit as x approaches 2, honestly approaches 2, not left or right, of f of x equals 9. But that equals the function's value at that point. So f of x is continuous at x equals 2. Okay? And that's it. So this showed me, right, I did my right limit, my left limit, which gave me the overall limit equaled 9. When I was doing one of them, I noticed that that would be the same computation as actually evaluating f of x at 2. So that told me that is also that same value, 9. But because those are equal, that tells me f is continuous at that point. So that's that. Hello. So in this example, we are again finding whether or not a function is continuous. In this case, we have this oh so nice piecewise function, right? This big mess. And we want to know whether it's continuous at 3. So again, as a quick sort of thought, I could say like, okay, is it even possible if the function exists at this point? So doing a quick scan, right, of the domains, I say, okay, 3 is landing in this one. So I'm looking at the middle function. If I were to plug in 3, does that work? So the x plus 6, that's just a a polynomial, that's fine. The natural log is a little concerning, right, because it has to have a domain strictly greater than 0. But if I plug in 3, I'm going to get 3 minus 2 is 1. That's in the domain, so that'll work too. So without actually necessarily computing it yet, I do know that the function will exist at that point. So again, I'm going to start with the limit part to see if the limit exists. And in order to know that, I need to compute, again, the left and right limit. It's typically sort of the way to go with piecewise functions because, again, unsurprisingly, this point, x equals 3, is landing in this nice, transition point here. So I'm going to be doing the left and right limits and seeing if they agree. If they do, then the limit exists. If they don't, the limit doesn't exist. And if the limit doesn't exist, it's not continuous and I'm done. If the limit does exist, that means I have to keep going. Okay. That's sort of the overarching goal here. So again, I'm going to start with the limit. As x goes to 3, let's do from the left first this time, of f of x. And I'll do the from the right in a minute. I'm just going to start with this one. So again, the limit from the left means I want things that are slightly smaller, right, than the 3. So I look at my list of domains, I say, okay, here this is x bigger than 3, more positive. That's not what I want. Indeed, I want over here where my x is less than or equal to 3. So particularly if it's a little less than 3, it's going to land in here. So I'm looking at this function, this middle function. So I'm going to look at natural log of, almost did it. Almost made that mistake. Right? I don't want to write the function yet because I'm still taking the limit. So this is the limit as x approaches 3 from the left. Now I write it. Natural log of x minus 2 plus x plus 6. And again, now that I have narrowed it down to which of the piecewise sort of segments that I'm working in, I can ignore the fact that the original function was piecewise and just work with this, right? And again, to be clear, this thing is going to be continuous because this is continuous, this is continuous. So the whole thing is continuous everywhere it's defined, which is going to be anything bigger than 2, which 3 is bigger than 2, so I'm good. So I can just plug this in and evaluate. So again, natural log of 3 minus 2 plus 3 plus 6. Natural log of 1 plus 9. And natural log of 1 is saying e to what power is 1, and that's 0. So this is going to be 9 plus 0 is just 9. Okay. So here I have computed my limit from the left. So now I'm going to compute my limit from the right. And you may note too, right, that this was where x equals 3. So this is also computing my value of f of 3 if I need that. So again, I'm taking the limit as x goes to 3 now from the right, so a little bigger than 3. So that's going to get me, right, this part here, this x being strictly bigger than 3, so a little bigger than 3 is going to land there. So I'm going to be using this function. So I'm going to be looking at, my brain is just misfiring all over the place. Try to do it yet again. Woo. Gotta keep an eye on me, guys. All right. So as x goes to 3 from the right, so I'm going to have x squared minus 3 to the x plus 1. And again, x squared plus 1, those are polynomial terms. 3 to the x, that's going to be a exponential. So this thing is defined everywhere, continuous everywhere. So I can just plug in my 3. Remember, this is positive 3. That's also positive 3, not negative, right? It's from the left and right. 3 to the 3 plus 1. That's 9 minus, so 3 cubed is going to be 27 plus 1. So 9 and 1 is 10, minus 27 is negative 17. But now I can see that the limit as x approaches 3 from the left, which is 9, is not the same as when it approaches 3 from the right, which is negative 17. So since the limit x approaches 3 from the right of f of x not equal the limit as x approaches 3 from the left of f of x, the limit as x approaches 3, the overall limit, does not exist. And if that limit doesn't exist, remember that means that it's not continuous. So f of x is not continuous at x equals 3. Good. So I don't have to compute f of x. I mean, I sort of already did, but if I hadn't done that, I wouldn't need to care because I've already determined that it can't be continuous, because once the limit doesn't exist, we're done. We don't have to move forward at all. Okay? So that's that. That's all there is to it. Hello. So in this video, we want to know whether or not our function, f of x, is continuous, specifically at this point, right? X equals -2. So remember, if we want to know if a function is continuous, what we're really asking is the three different parts, right? Like whether the limit exists, whether the function exists at that point, and whether those two things are the same. So we could go through the process of figuring out the limit, then through the process of figuring out whether or not the function exists, and then see if those two things are equal. I typically like to do it the other way around because it's usually pretty easy to figure out whether a function exists at a point, because we can just plug it in and see if it's well defined. So for my function here, I'm basically going to start by checking that. So I'm going to check I want to check sort of, again, in general, the limit existing, but first I'm going to start with, does f of my point, -2, exist? Because remember, I need all of those things to be true, and so if this doesn't work, then I'm done. I don't have to worry about doing any of the limit stuff, right? So I'm just going to plug it in and compute. So f of -2 is, so my f of x is up here, right? So I'm going to have this -2 squared plus 3 times -2 plus 2 all over -2 cubed plus 6 times -2 squared and plus 8 times -2. I guess I didn't make my bar quite long enough. There we go. So again, all I'm doing is plugging it in. I want to see if the thing is well defined at this point. So now I'm just going to plug and chug. Go ahead and compute, right? So this is -2 squared is 4. 3 times -2 is -6 plus 2 over -2 cubed is going to be -8. 6 times -2 squared, so that's 4 times 6 is 24. And 8 times -2 is -16. 4 minus 6 plus 2, so that's going to be 2 and 4 is 6, minus 6 is 0, over -8 and -16 is -24, plus 24 is 0. So if I plug in -2, I get 0 over 0. So if I were computing the limit right now, that would tell me that I have this indeterminate form, meaning that I'm going to need to factor this thing and, you know, cancel out a common factor and see if I can sort of resolve this issue. But I'm not computing the limit right now, right? So what I'm doing at the moment is I'm trying to get this, see if this function exists. And whether I could cancel out a factor or not actually doesn't matter here, because the fact that I'm trying to divide by 0 means that f of -2 is not defined, right? -2 is not in the domain because it makes the bottom of the denominator 0. So this tells me f of -2 does not exist. It's not defined. And that tells me, this line tells me, so f of x is not continuous at x equals -2, because it's lacking one of those features, right? This idea that it has to have the limit exist, have the function exist, which it doesn't, and thus, if one of those fails, function doesn't exist at that point, it's not continuous. And that's it. I didn't have to do any limits, didn't have to do really any calculus-y stuff, right? This is all pre-calculus, or arguably even just, algebra 2, because all I did was evaluate the function and notice that it doesn't exist there. Okay, so when you're looking for continuity, don't overthink the problem, right? Check the easy stuff, because if it works out, then you don't have to do any of the hard stuff. Okay? So that's that.